So there are two basic operations when we work with stack, push and pop. But we need to understand the condition for pop and push. Firstly, if you want to work with push and pop, we need to know the size of stack. This is the number of data entries in stack. That means the first address of stack and the last address of stack. For the example, the first address of stack is 1400. We can call it the bottom of stack, and in fact, we could use the location at 1400. And the last address of the example for stack is 3FFB. Besides, for the top of stack, this is the stack pointer to point to the data item on the top of stack. With the LC-3, this is a 6. So over here, you can see the pop subroutine with underflow detection. You know, when you pop a data item out of the stack, you should check if it's empty or not. So over here we have an empty, and we have the value for the location at the address empty, COOO. This is minus, this is negative 1400. You remember 4000? This is the address of both, that means bottom of stack. So over here, firstly, we assign it to R1, and then we add between R1 and R6 to get the value, and we assign it to R2, and we check it if it's 0 or not. If the value in R2 is 0, so that means R1 and R6 they are equal to each other at that time. The set is empty, so we are failed. Okay, so at that time we go out and we return value 1 to say no, we couldn't work with stack because it's empty. Okay, and when we go out, that means it is okay at that time, because you want to pop a data. So firstly, you need to read it out from the base register R6 and the offset 0, and we take the value over here and we assign it to R0, and then we increment the stack pointer R6 to point to the new data we can get out, and then we return value to say okay, it's okay, we should read out a value from stack and return. And with push we have overflow detection. Okay, and over here the extension we also use the register R5 to say 0 or 1 if 0 success, with 1 for overflow. That means we couldn't put in the other value to the stack because the stack is full. So over here we have value marked COO5. That means minus 3FFB and negative 3FFB. This is the last address or the last location. With the figure, now firstly we say now as it the stack point, so now we're storing the value 1400. This is the address of this, or we call it both. Okay, so we have 4000, 3FFF, 3FFE, 3FFD, 3FFC, and 3FFB. That means we have four locations in stack, and we can use them to store our value data item. Okay. And over here the same, so we compare, that means we use the between this value and the substitute R2 to get it now. If they're equal to each other, so it's 0, the value 0 in R for R2, okay, and that time to go out because we are far. But when we keep going down, so because over here we are doing push, so firstly we need to decrement the step pointer to point to the numeration, and then we have to put in the new value from R0 to the location from the base R6 R0 over here. And it's okay, so we assign 0 to R5 and then return. Now we go to the next section, interrupt driven I/O part 2. You know, in chapter 2 when we study I/O, you didn't study a lot about interrupt, but now when we go to the chapter, you study the mechanism how to use the interrupt, the mechanism how to get it. So firstly, you should understand what interrupt is. You know, when we work with an output device, so we call them external devices, and they have some signals and they need to be serviced. At that time, processor self-states and starts service routine for reporting to the external devices or input-output devices. And when finished, processor restores states and resumes program. So that time we say interrupt is an unscripted subroutine call and is triggered by an external event. So over here we say processor state, and we need to shut them when we go to interrupt service routine. So the first is processor stated register PSR. So there are some fields over here, and you need to pay attention to the first, the privilege, the privilege bit, so bit 15 of PSR. You know, when the privilege is at 0, you are in the supervisor mode, and when it's 1, you are in user mode. And we have 3 bits for priority level, and there are 3 bits from bit 8 to bit 10. And there are 3 bits for LGBs over here. And besides, we have program counter PC and virtual sound. When we go to interrupt service routine 2, besides we have some register. But where to show processors that, you know, because we don't know when we have interrupt, so we can't use register. We can't prepare the register, what register, because over here we don't know when the interrupt happens. We don't know, so we can't prepare. Okay, and besides, we don't know where to prepare. So at that time, we should use steps. It's so convenient. Okay, you will study, you see. So firstly, you know the supervisor stuff. Okay. So over here I give you the picture for the memory map of the LC-3 with interrupt vector table and the supervisor stuff over here. And you know, because when we go to interrupt subroutine, at that time you need to store many things. So normally we use supervisor stuff to do this. So supervisor stuff, that is a special regions of memory used as the stuff for interrupt subroutines. And we have some pointer we need to store them when we go to interrupt subroutine. So that is supervisor stack pointer, and we use self as a P to store them. And store, and we use self USB for storing user stack pointers. Okay. And of course, we need to use that pointer asset because we have to return after having done the interruption routine